The next speaker is Pablo Jarillo. Pablo Jarillo-Herrero is a full professor of physics at MIT. He obtained his PhD in Delft University in the Netherlands, and his research interest lie in the area of experimental condensed matter physics, in particular quantum electronic transport and optoelectronics in novel topological materials, with a special emphasis on investigating their superconducting, magnetic, and topological properties. Pablo, whenever you want, you can get started. I want to remember that Pablo's talk is 45 minutes, and then we will have 10 minutes discussion questions. So you can post your questions in the questions and answer chat. So thank you very much.
Okay, thank you, everyone. Can you hear me well?
Yes.
Okay, very good, excellent. So I want to start by thanking Sergio and the rest of the organizers for the invitation. I just wish I could be there in person. My background is actually the beach in Barcelona, where I wish I was, or at least close to, so that we could go after the conference. So I want to tell you, the title of my talk is Moire Magic 3.0. What I want to tell you about is about the next generation of Moire quantum matter that we're investigating in my group. And I will, I will start by, remind you, probably most of you are familiar with this, over the past few years, a new platform has emerged for strongly correlated and topological physics, which is Moire quantum matter, okay? This is a nice complement of to our other two platforms that we have to do this type of physics. One is actual quantum materials, okay, with a lattice scale of a few angstroms. The other one is ultra cold atoms in optical lattices with a typical length scale of about a micron. Okay, these two platforms have existed. This one for many decades, this one for about 2 decades. In the past few years, we have this Moire quantum matter where the natural length scale is sort of intermediate between these other two platforms, and it's supported 10 nanometers. Okay, now the thing that initially enabled, possibilitated this Moire quantum matter platform was the fact that with two-dimensional materials, we can do the following. We can twist two-dimensional crystalline structures at an arbitrary twist angle between the crystalline lattices, okay? That's something that is unprecedented in the history of material science. We could not do it. We could not do it before the advent of 2D materials. And the electronic, optical, mechanical properties can vary dramatically when we do these rotations. Now, why would one study, Moire quantum matter? What does it offer, okay, as a platform? So first of all, it's an easy way to obtain isolated flat bands. Okay? When you have a flat band, you have very little kinetic energy. So then interactions acquire a more prominent role. So to investigate the interplay between kinetic energy interactions and also topology, okay, these flat bands are very useful. Now, the other thing is that with a few simple building blocks, for example, graphene or hexagonal boron nitride or transition metal dichalcogenides, these, you can have a range of heterostructures that give you a plethora of correlated and topological behaviors, okay? Which brings up the question of, what are the key essential ingredients needed for complex emergent behavior of quantum matter, okay? Because again, to some extent, we can get rid of a lot of chemistry by using these very simple blocks and still obtaining the more, the type of behavior which is more typically associated with very complex chemistry, for example. Now, this platform is highly tunable in situ. Okay, we can apply electric fields, electrostatic doping, strain, pressure, magnetic temperature, and of course, you can also tune it through twist angle or the type of Moire system. And finally, it's a novel experimental platform to explore vast new families of hybrid materials based on non-equilibrium growth and assembly. Okay, so a lot of interesting new physics has emerged, and plenty more is coming out, every month. So this, this has led to this sort of the magic of Moire quantum matter, which is the fact that, again, with just a few very simple building blocks, we have been able to already obtain most of the phases of condensed matter physics. Okay, and usually with very special twists. So we have, correlated insulators have been seen in a variety of Moire heterostructures, also superconductivity, various topological phases, magnetism, pneumaticity, and even ferroelectricity. Okay, and we keep discovering more and more phases, you know, in these Moire quantum systems. Now, the phase that has arguably attracted the most attention is superconductivity. Okay, and just a few months ago, you know, my group and also the group of Philip Kim, we published back-to-back, you know, the same week in Nature and Science, the discovery of a new generation of Moire quantum systems based on three layers of graphene. These are, you know, tunable, you know, these systems are magic angle twisted tri-layer graphene. It's a much more interesting and richer system than the bilayer counterpart, okay, which some of you may have heard about. And this is basically what I want to be telling you about today. So this is the outline of my talk. I'll start with, you know, describing graphene and magic angle graphene and a little bit about Moire quantum matter. And here is where I will mention some of the recent developments in topological physics, okay? But then I will move on to Moire Magic 3.0, magic angle twisted tri-layer graphene, and show you that it's a highly tunable superconductor that realizes ultra-strong coupling. Now, I miscalculated the time that I had for, or I misunderstood the time that I had for the talk. So maybe I will get to this unexpected surprise or not. Okay, if not, it doesn't matter. You know, there's plenty of other things that I will be telling you about. And I'm sure I will not get to the outlook, so we can discuss about outlook during the discussion session later on. All right, so let's start with magic angle graphene and Moire quantum matter. And for that, we start with the basics, with graphene. So graphene is a honeycomb of carbon atoms. Okay, all of these atoms are, from the crystallographic point of view, identical. They're all carbon. Sorry, from the chemical point of view, they're all identical. They're all carbon. But from the crystallographic point of view, there are two inequivalent atoms. We call them the A and B sublattices, or red and green balls here. Okay, that's because to tile a honeycomb into dimensions, you need two unit vectors and a two-atom basis. You can calculate the electronic structure of graphene in a simple tight binding, you know, model, and you get this very unusual electronic structure where near the Fermi energy, you have these double cones. They're called the Dirac cones, where the energy versus momentum relation into dimensions is linear. Okay? This can be formalized in a Hamiltonian equation. This is nothing else but the Dirac equation in two dimensions for massless particles. Now, in the usual Dirac equation, the spinor represents the spin up and spin down of the electron. Here, it represents whether the wave of the electron wave function is a pseudospin, which represents whether the weight of the electron wave function is on the A or B type of sublattice. Now, the other thing that I want you to remember is that we have two inequivalent, you know, Dirac cones or valleys. They're called the K and the K prime valleys. Okay, and this will play a role in what I will be telling you later on. So electrons in graphene have this fourfold degeneracy: spin up, spin down, valley K prime. Now, what happens if you put graphene on top of graphene and you rotate the angle? A Moire pattern forms, okay, where the Moire wavelength, the distance between the soccer balls that you see in the screen, is actually roughly inversely proportional to the twist angle. Okay, so you form a super periodic structure which has this Moire pattern with a very long wavelength, okay, at small angles. Now, let me stop this before you get dizzy. This is what happens in real space, what happens in momentum space, and therefore what happens to the electronic structure, okay? So let's start with a small angle where already the distance between the Dirac cones in momentum space, these are the Dirac cones from layer 1 and from layer 2, is proportional to the twist angle. Okay, now this would be a situation that would occur if these two Dirac cones did not know, you know, if these two graphene sheets did not know about each other. However, the electrons in these two graphene sheets are only spaced by 3 angstroms, so they're very much aware that the other graphene sheet exists, and in particular, they can tunnel between the sheets. Yeah? So that leads to bonding anti-bonding states, okay, similar to the hydrogen molecule, but now in a giant graphene, you know, molecule, okay, where this interlayer tunneling, you know, leads to a band repulsion here, okay, to the opening of a gap. This is the situation that occurs when this crossing point of these energies is much larger than the interlayer tunneling, okay? But as you decrease the twist angle, this crossing point goes to lower and lower energies. So this band gets pushed down and down to lower and lower energies until it gets pushed down flat to 0, okay? At that instant, we say that a flat band condition has been reached, and it's reached at the magic angle, which happens to be for graphene on top of graphene, 1.1 degrees. It depends on that interlayer tunneling. Right? So this 1.1 degree and the existence of these flat bands at the magic angle, was theoretically predicted about a decade ago by physicists in McDonald, also interesting work by Suarez Moire and collaborators. And there was already experimental evidence at the single particle physics level that indeed something happens at that angle, okay, by STM measurements in the group of Eva and Ray. Now, let me show you, what you saw before was a cartoon. This is an actual calculation of the electronic structure versus momentum, okay? This is a set of flat bands, okay? And these are the other Moire mini bands, okay? The other remote bands, which results from the folding of the band structure because of the Moire periodicity. These flat bands, okay, as you can see, they're not perfectly flat, okay? But they are orders of magnitude flatter than the original graphene dispersion. Now, this is how they look in momentum space. If you want to see where does the charge go when you put electrons in these flat bands, you have to do a Fourier transform to go to real space. And then what happens is that you can see that when electrons are in these flat bands, they like to sit in these regions where locally, okay, the two graphene sheets appear to be exactly aligned and on top of each other. We call this AA stacking, okay? These regions are tunnel coupled by regions of AB and BA stacking, where due to the small angle of rotation, the graphene sublattices from layer 1 and layer 2 get out of registry into this AB and BA configuration. Yeah? So schematically from the top, twisted bilayer graphene looks like this. You have these regions of AA stacking. They form a hexagonal structure where the electrons like to sit. And then you have the regions of AB and BA stacking, which form a honeycomb pattern where the electrons do not like to sit. Yeah? So in a slightly more realistic schematic, these regions of AA stacking are spaced by 13 nanometers at 1.1 degree angle, okay? And this forms the equivalent of a triangular Fermi-Hubbard lattice by analogy with the cold atom systems, except that it's triangular in quotes because in reality, this is a honeycomb structure because of these AB and BA regions. And also, this structure has interesting topological properties, as I will mention in a moment. So it does not really offer a direct mapping to a standard Fermi-Hubbard lattice that you can isolate into isolated atoms. This actually has topological properties that prevents that direct mapping. So, and then what my group discovered a couple of, 3 years ago now, is that when you populate, with the chemical potential of those flat bands, you can have unusual correlated insulator states at fractional fillings of those flat bands. And if you dope a little bit away electrostatically from those fractional fillings, you get superconducting domes, okay? Magic angle twisted bilayer graphene is an electrically tunable superconductor where you can have various types of superconducting domes in the system. This all happens for a small range of twist angles around 1.1 degrees, something between 1 and 1.2, maybe 0.9 to 1.3 degrees, this type of physics. Now, so we posted, we published our paper officially in April 2018. We announced a month earlier at the APS March meeting. So what has happened since then? Okay, well, the first thing that has happened is that we have reproduced our own results, many times. Believe it or not, that doesn't always happen. So it's good that you're able to reproduce yourself. So by now we have, dozens and dozens of devices. In fact, we're starting to map what is the critical temperature at optimal doping as a function of twist angle. This is a new tuning knob, okay, in condensed matter physics, the twist angle between two heterostructures. Now, even better than you reproducing your results is when others reproduce it. And by now, many, many groups have independently reproduced our results and extended them to many other very interesting systems, okay? This includes, very well-known work at Barcelona and at many other places. Now, we have also discovered many other correlated systems. For example, the second one, which was based on this Swisstronic platform, was magic angle twisted bilayer graphene. So now we also have a structure with 2 layers, but each of these layers is a Bernal stack bilayer graphene. Okay, so we have now in total 4 layers of graphene, 2 with no misalignment, 2 with no misalignment, and then twisted pairwise with respect to each other. That system gives you interesting correlated magnetic states, for example. Okay. Now another thing that has happened is that people, are starting to use different scanning probe techniques, scanning probe microscopy techniques to look microscopically at what happens at these heterostructures. Okay, and it started with very interesting scanning tunneling microscopy work, but people have done since also scanning near field optics, scanning SCT, scanning nanosquid, and they're applying all these techniques to this very 2D platform, which it lends itself very well to investigation by scanning probe microscopy techniques. One thing that I want to mention regarding these scanning techniques is that it has allowed us also to start to investigate the thermodynamic properties of these structures, okay? So let me particularly tell you something about this. So initially, for the first few experiments for the first year or so, the knowledge that we had about the first couple of years about magic angle twisted bilayer graphene came mostly from global electronic transport measurements, okay? And this is what we had obtained, as samples evolved and we got more and more data. You have, in a phase diagram where you have temperature here and filling factor on this axis. This filling factor is the same as charge density, which we control electronically, okay? This filling factor is telling you what is the number of electrons or holes that you have per Moire unit cell, okay? It turns out in these flat bands, from bottom to top, you can put up to 8 electrons per Moire unit cell. From charge neutrality, we say that we can either go to the top of the conduction band and fill 4 electrons per Moire unit cell, or we can go to the bottom of the valence band and we can fill it with 4 holes per Moire unit cell. So -1, -2, -3, -4 means 1, 2, 3, 4 holes per Moire unit cell. 1, 2, 3, 4 holes, electrons, sorry, 1, 2, 3, 4 electrons per Moire unit cell here on this side, okay? Now, when you either fill with 4 holes or 4 electrons, you reach this band gap. So at 4 and -4, you have band insulators. These are single particle band insulators, okay? But then as you fill each integer number of electrons per Moire unit cell, something interesting happens, okay? At 2 and -2 and at 3 and sometimes at -3, what you see are correlated insulator or correlated semi-metal states. At 1 and -1, you have correlated semi-metal states. At 0, at charge neutrality, you have a Dirac semi-metal or a Dirac insulator state, depending on details, okay? And then as you dope away from 2 holes per Moire unit cell or 2 electrons per Moire unit cell, you have superconducting domes. This is usually the biggest, the most prominent. When you dope with extra holes, the correlated insulator state at 2 holes per Moire unit cell. Now, this is what we knew from global electronic transport measurement, okay? So then 2 papers appeared last year, okay? One, it was from my group in close collaboration with a group of Shah Halilani at the Weizmann Institute. The other one was by the group of Ali Yazdani, where they obtained very similar results using scanning tunneling microscopy. And more recently, we have also obtained related results using global chemical potential measurements with a graphene sensor. I'll mention a little bit later. So in the group of Shah Halilani, they have developed this very interesting technique where you have a carbon nanotube, which acts as a single electron transistor. They have it at the tip of essentially an atomic force microscope. And then they can scan with this tip across the device, and they can measure locally the chemical potential, okay? In particular, they can measure the derivative of the chemical potential with respect to density, which is called the inverse compressibility. The compressibility is the derivative of the charge density with respect to chemical potential, and is in single particle physics is the density of states, proportional to the density of states. The inverse, d mu dl, inverse compressibility, you can think of as the inverse of the density of states, okay? So gaps, Dirac points, they appear as peaks, okay? So what Shahal and his collaborators saw is that if you scan on a magic angle twisted bilayer graphene device, where they can go locally to different regions where different twist angles, as a function of filling factor, they observe a sequence of sawtooth type of behavior, okay, which we call a cascade of phase transitions, okay? Let me show you here, zooming in some of the data at 1.13 degrees, okay? You see that at each integer, okay, you have a feature, a sawtooth-like behavior. Turns out, to 0th order, okay, you can understand this feature in the inverse compressibility that occurs at each integer as spontaneous flavor polarization. And by flavor, I mean spin or valley, okay? Remember that spin and valley degree of freedom of spin, okay, of the system due to strong electron-electron interactions, okay? So in a very simple picture, what you can think of is the following. I have these 4 flavors, spin up, spin down, valley K prime. And when I start from charge neutrality, okay, those flavors, as I add charge to the system, start getting filled. Initially, all of these flavors get filled at the same time, okay, at the same rate. Now, when I'm close to filling factor, total filling factor 1, that means when I have about 1/4 of each flavor filled, okay, the system spontaneously flavor polarizes, changes, sends all the carriers to one flavor and empties the other 3 flavors, okay? It becomes flavor polarized. Then the same process starts again. I start filling the other 3 flavors, close to nu = 2. The system decides to, again, spontaneous flavor polarizes 2 flavors, polarizes 2 flavors, and then 2 of the flavors becomes empty, etc. These phase transitions that take place due to strong electron interactions form this cascade at each integer. And in a simple model, you can see that this gives you an inverse compressibility, which has a sawtooth type of behavior, okay? And there are more refined models nowadays that account better for this behavior, but the essence is a sequence of phase transitions due to strong electron interactions, which lead to flavor polarization of your bands, okay? So this couples with what I'm going to tell you now. So the other thing that was, one of the most interesting developments, after our discovery was the discovery of ferromagnetism, anomalous Hall, and quantum anomalous Hall physics in the system, which brings the role of topology front and center, to the physics of Moire quantum matter. Okay, so in fact, this Moire, quantum matter platform has meant emerging of several modern condensed matter physics communities. On one hand, you have people that did 2D van der Waals materials and heterostructures, people that did graphene, people that did strongly correlated, materials, like cuprates, pnictides, etc. And the people that did topological condensed matter physics, fractional quantum Hall effect, or topological insulators, all 3 of these communities come together into this field of Moire quantum matter. Okay. Now, I'm going to mention only a few words about this, but these are the bands of magic angle twisted bilayer graphene. Okay. Now these bands are, there are several sets of bands here, again, because of the valley degeneracy, okay, and sublattice degeneracies too. So you have these degenerate bands, which, do not, they're not capped, and they're very flat. Turns out, if you break C2T symmetry, where C2 stands for 180-degree rotation around an axis, a Z-axis, an axis perpendicular to the graphene plane, okay? So a rotation of 180 degrees. And T is time reversal symmetry. So if you break the product of C2T, then these flat bands become gap, and these have different Chern numbers. Okay. Now you can do this in various ways. For example, you can think, oh, let me break the C2 symmetry. Okay, and then you have a set of 8 bands with Chern numbers, and where there is valley asymmetric Chern number between the K and the K prime valleys. You can break actually time reversal symmetry instead, and then you have a valley symmetric Chern number situation. Okay, and part of the complexity and the richness of the system has to do with these different possibilities and with interactions leading to small symmetry breaking terms that that can and small symmetry breaking terms that can lead through interactions to breaking of degeneracies. Now, already in 2019, together with my theory collaborators at MIT, we discussed that the existence of these nearly flat Chern bands in Moire superlattices. These were various types of Moire superlattices, where the key aspect here was the breaking of the C2 symmetry. So these were superlattices which were aligned to hexagonal boron nitride. And there was plenty of other work, a little bit earlier related to the fragile topology of magic angle twisted bilayer graphene, and also this type of structures. So within, very soon, within a few months, the group of David Haber-Gordon, they were able to realize anomalous Hall effect, okay, in magic angle twisted bilayer graphene aligned to HVN. So where you break the C2 symmetry because you have the hexagonal boron nitride, okay, which makes, inversion symmetry aligned to the twisted bilayer graphene. And then, the following year, the group of Andrea Young published this very interesting experiment where they actually measured the quantized anomalous Hall effect, okay? So quantum Hall effect at 0 magnetic field in, again, magic angle twisted bilayer graphene aligned to the hexagonal boron nitride. And again, you can understand this. This was a filling factor of 3, okay, where we had gone through this cascade of phase transition, and all there was is one, flavor polarized band to be filled, after nucleus +3, okay? Now, you can instead break time reversal symmetry. So by now, several groups have observed the existence of Chern insulator states in the presence of a finite magnetic field which stabilizes the Chern insulators, okay? And you can see a very interesting sequence of Chern insulators with Chern numbers 1, 2, 3, 4, 4 filling factors 3, 2, 1, 0, okay? Again, all of these 1, 2, 3, 4, etc. have to do with this 4, degrees of freedom Valley spin that I told you earlier. Yeah? You can do this in the presence of a finite magnetic field. More recently, and by the way, sorry, I should mention that together with my collaborator, Ray Shuri, we had published earlier this paper where we measure the quantum capacitance of magic angle twisted bilayer graphene devices, not aligned to HBM, okay? And we saw this sequence of what we know now are Chern insulator states with slopes of Chern numbers of 1, 2, 3 at filling factors 3, 2, 1, etc. Okay. Back then, we identified the host of the butterfly physics of the system, but not the nature of Chern insulator nature. So that was, a oversight. We should have spoken to more theorists about this, and we didn't realize it. But it was already present, those Chern insulators in this data clearly. Now, more recently, people have realized that the C2T symmetry can be broken without H-in alignment and at zero magnetic field. Just interactions themselves can spontaneously break C2T symmetry and lead to this type of topological physics that I'm mentioning, okay? So for example, the group of Dima Efetov at ICFO has shown that you have these strongly anomalous, not quite quantized, but very high anomalous Hall effect, in structures which are not in principle aligned to hexagonal ornithine, and they can see this anomalous Hall effect at zero field. Okay, the group of Alias has also shown in a very interesting experiment, STM experiments, how interactions can break spontaneously that C2T symmetry. More recently also, we have applied a new technique, okay, using chemical potential, but not by using scanning SET, as I mentioned with the group of Shahalilani, but now we can have our magic angle twisted bilayer graphene next to monolayer graphene. And by tracking the charge neutrality point of monolayer graphene in a dual gated structure, okay, this is the band alignment of the system, you can actually measure the chemical potential of the magic angle twisted bilayer graphene. Okay? Now, when you measure that chemical potential, here's a measurement, for example, of the chemical potential as a function of filling factor, and at varying magnetic field, you can see steps in your chemical potential. Those steps correspond to the Chern insulator gaps, okay? So we're measuring the Chern insulator gaps, okay, as a function of magnetic field. And here you have, the values of those gaps. So these are the first thermodynamic measurements of the Chern insulator gaps, which you cannot use, measure those gaps in a transpose experiment. You can do a thermal activation, but it usually doesn't give you as much information. So the last thing that I want to mention is that not only you can have that sequence of Chern insulator states at 1, 2, 3, 4, with Chern numbers 3, 2, 1, you can also have interactions can give you different sort of unconventional sequence of Chern insulator states. Okay, this is now scanning single electron transistor, similar to the one that I mentioned before with Shahalilani, but it's in the group of Amir Jacobi, and it's with a metallic SET. Again, they can scan these over our sample, our devices, okay? And they can locally measure the inverse compressibility, as you can see here. And now you can see that this is a much richer pattern that I showed you before in the case of Shahalilani, okay? This is filling factor, this is magnetic field. And now you have a very interesting pattern of Chern insulators and quantum Hall insulator states, okay? Here you can see the black lines are integer quantum Hall insulator states. And then you have various types of Chern insulators, okay? The red and the blue lines, okay? Which do not conform, before from 1, we should have a Chern insulator with 3 slope, from 2, 1 with 2, which we see here, from 3, 1, 2 with 1, that we see here, but we see plenty other Chern insulator states. That unconventional sequence of Chern insulators has to do partly with the fact that interactions can give rise to translational symmetry breaking, okay, spontaneously due to interactions, or otherwise the formation of charge density waves in the system. Okay? These are called symmetry broken Chern insulators. And I don't want to tell you too much about this because I see that I'm running out of time, but you can go to this paper and you can see how a doubling of your unit cell due to interactions can split your Chern bands into bands with trivial bands and bands which continue to have Chern number. And by populating the different sequence of Chern bands, you can obtain all the sequence of anomalous Chern insulators that I told you earlier. The last thing I want to mention is that the next generation is in this Chern insulator and the topological properties of graphene would be the observation of fractional Chern insulators. Okay? If Chern insulators are the zero magnetic field equivalents of quantum Hall states, fractional Chern insulators are the zero magnetic field equivalents of fractional quantum Hall states. So they're much richer and deeper in physics and topologically. And one of the holy grails or major breakthroughs that we would like to see is that the observation of fractional Chern insulators, fractional quantum Hall states at zero magnetic field. Okay. Now, in the next 10-15 minutes, I want to tell you about magic angle trilayer graphene. Okay, this is mostly what I'm going to be telling you, not related to topology, but this is very recent system. There is, of course, Chern insulator states and it's topology that will be measured here and reported soon. So, the structure that I want to tell you about again is this new generation of Moire quantum matter. Is mirror symmetric magic angle twisted trilayer graphene. Okay, so that's quite a mouthful. Let me show you what I mean. These are 3 layers of graphene on top of each other, where if you start from the bottom, you start with 1 layer of graphene, then you rotate by an angle minus theta, the second layer, and then you rotate by an angle theta with respect to the middle one, the top layer, such that the top layer and the bottom layer are exactly aligned on top of each other. This was a configuration proposed by Eslam Khalaf in a group of Ashwin Vishwanath, and it's called A twisted A stacking, because the bottom and top layer are not only perfectly aligned, they're also atomically all atoms on top of each other, okay, between the bottom and the top. Now, plenty of other work, related to mirror symmetric MATTG has been published, and related work on twisted trilayer graphene and multi-layer systems too. Now, this system, magic angle twisted trilayer graphene, has a very interesting electronic structure, okay? If you think of these 3 layers with interlayer tunneling T between the layers, it turns out you can, the Hamiltonian of this system, you can make a rotation, a basis transformation, such that it becomes block diagonal, where one block is magic angle twisted by layer graphene-like block with an effective square root of 2 times T interlayer tunneling, and the other block is just a monolayer graphene block, okay? This means that, remember that I told you before that the magic angle condition depends on the interlayer tunneling. Because of this square root of 2, the magic angle for magic angle twisted trilayer graphene is that of the bilayer case times square root of 2. So it's 1.1 times square root of 2. So it's 1.56 degrees. Because of this, the Moire wavelength, the angle is a little bit larger. So the Moire wavelength is a little bit shorter, okay? 9 nanometers instead of 13 nanometers. And this system probably has a little bit stronger interactions, okay? Now, this is the electronic structure, okay? When there is this, mirror symmetry, both structurally and also electrically, all the 3 layers are at the same potential, then, or at zero displacement field, then the energy versus momentum gives you these 2 set of bands, bands. The orange ones are the magic angle flat bands. The flat bands corresponding to the magic angle twisted bilayer graphene-like sector, okay, or block. And this Dirac cone corresponds to the monolayer graphene sector, okay? Now, that was the situation when all 3 layers are at the same potential. In our devices, we have the magic angle twisted trilayer graphene. It's contacted by source and drain electrodes in a whole bar geometry. And then we have a bottom and a top gate. With these bottom and top gates, we can independently control the charge density or filling factor by applying, for example, the same polarity to those gates. And independently, we can control the transverse electric displacement field, okay, by applying opposite voltage to those 2 gates, okay? And when we apply a finite displacement field, then we break electrically the mirror symmetry in the structure. And then we can hybridize the massless Dirac bands and the flat bands, okay? And we can hybridize them to form this interesting electronic structure, which is tunable with displacement field, the degree of hybridization, okay? So, okay, the first thing I want to show you is that the system is a robust superconductor. So for that, you want to see zero resistance, and indeed, resistance drops to zero. You can fit this with the Halperin-Lenz formula. It tells you the Berezovsky-Kosterlitz transition, which in this case is about 2.3 Kelvin. Sometimes we quote 50% on mass resistance in this two-dimensional community, and that's 2.9 Kelvin. Now you want to see flat voltage current characteristics with sharp switching. And indeed, you can see here that you have a finite critical current with 0 voltage dissipation, and then it switches abruptly to a normal state, okay? You can do this as a function of temperature. You can analyze this to obtain independently the VKT temperature, which agrees with these measurements. Then the system is also an electrically tunable superconductor, similar to a magic angle twisted bilayer graphene. If you fill around 2 holes per model unit cell, you can fill with extra holes and you have superconducting dome. You also have a superconducting dome at -2 plus delta, where plus delta means a few electrons with respect to the 2 holes. You can do the same thing around 2 electrons per model unit cell, also 2 superconducting domes on this side, okay? We control all of this electronically. Now, you also want to see what happens in the magnetic field. So if you are near optimal doping, where superconductivity is very robust, if you measure the differential resistance as a function of current bias and magnetic field perpendicular to the plane, then you can see, black means, critical current. So, I mean, the region, superconductivity. So you have this critical current, which has a long tail, gets initially suppressed on a 100 millitesla scale, but then it has a long tail up to about half a Tesla, okay? If you now tune electronically your system to the boundary of the superconducting dome, where the system is barely superconducting, the system tends to divide itself into superconducting and non-superconducting islands, which can give rise to Fraunhofer-like oscillations, okay? Meaning that there's just some phase coherence in your system. So this unambiguously proves that you have, a superconducting system. Now, let me show you that this is a very highly tunable system. So, as I said, this is highly tunable. So we have this independent density of filling factor and displacement field. Okay? So this is what the resistivity versus filling factor and displacement field looks like. Okay, it's a very complex phase diagram. Let me guide you. Superconductivity occurs, is these light blue regions. Those are the superconducting regions. And resistive features are in yellow. These are highly resistive features, okay? As you can see, this diagram has certain symmetry. First of all, top to bottom, okay? So you can see that these branches, they appear, these features, there's symmetry top to bottom. That means that twist angle between the bottom and the middle and the top and the middle layers are very similar, okay? Otherwise, you would have displacement field would give you an asymmetry. You also have certain degree of symmetry between the right and left parts, okay? For example, superconductivity occurs mostly between 2 and 3 holes per model unit cell and between 2 and 3 electrons per model unit cell, but you have these branches also, which are largely left-right symmetric, okay? Now, you could also focus on the asymmetries left to right. For example, you have resistive features here that are absent or very weak on this side, okay? In fact, this left-right certain degree of asymmetry is very reminiscent of what happens in magic angle twisted bilayer. There is also an asymmetry between orbital electrons and orbital holes from charge neutrality. Yeah? Now, we can measure other quantities in the system, okay, and see if they correlate with the superconducting regions. So in particular, we decided to measure the normalized hole density, okay, nu H. This is the hole density equivalent of the filling factor of the regular density, okay? So this is the hole density, which we measure via hole measurements. So measurements of RXY at small magnetic fields, okay? And then we normalize by the superlattice density, the number of electrons that fit per more unit cell and multiply by 4. So that it is the equivalent of nu filling factor, but for the hole density, okay? So then when we measure this, we have also this complex phase diagram as a function of displacement field and filling factor. And to zeroth order, all of the features here can be associated with one of the following three situations. Okay? If you have a gap Dirac point, your Hall density goes smoothly through zero and changes sign going smoothly through zero. Okay, because your density of carriers that can contribute to conduction, that's what your Hall density tells you, okay, disappears at a gap point or a Dirac point, okay? So that happens, for example, here across charge neutrality, okay? You can also have a reset of your Hall density, of your normalized Hall density, that occurs in those phase transitions, that occur at integers, or it can occur there, okay? So you can go from low Hall density to higher, and then a drop near zero, and then it starts growing again. This can happen in red or in blue. Let me show you an example in blue here. You go from light blue to darker blue, and then reset to white, to zero, and then light blue, darker blue, okay? And then you can also have Van Hoff singularity type of behavior, where your normalized Hall density flips sign, but diverges before it flips sign, okay? So, for example, you can go from light blue to dark blue, abruptly switch to dark red, and then to light red. And that happens here, for example. Light blue, dark red, light red, okay? So in this diagram, to zeroth order, again, most features can be associated with one of these conditions. So now let's compare these two diagrams, okay? And I'm going to do that schematically. So this is the regions, these are the superconducting regions that we saw before, okay? And now we can look at what are the Hall density features. So these regions are where gap Dirac type of behavior transitions are seen. The orange, we have the reset type of behavior. And in dark blue, we have the Van Hoff singularities, okay? And as you can see now, a pattern emerges where superconductivity is mostly bounded by resets at low displacement field, but it's bounded, the boundary is set by Van Hoff singularities at large displacement field, okay? So let's examine that a bit more closely. So I'm going to show you trace cuts along this Van Hoff singularity here, okay? So we can measure the resistivity, of course, superconducting state until it comes out of the superconducting state as I cross the boundary. I can measure the critical temperature as a function of filling factor. It's finite here, and then it's zero the moment it stops doing superconducting, of course. Then I can measure also my effective mass, which is proportional to the density of states as a function of filling factor. You can see that it diverges, on both sides of this point. It has a cusp here and decreases on both sides of this point. That point corresponds to the Van Hoff singularity, where you expect indeed your density of states to diverge, okay? And the interesting thing is that the Van Hoff singularity corresponds to the boundary when TC becomes zero. And moreover, as you approach from this side, the Van Hoff singularity, your density of states is increasing and increasing and increasing, but your critical temperature is decreasing and decreasing and decreasing until it becomes zero at the maximum density of states, okay? So that's very much unlike weak coupling BCA type superconductivity, okay? Where your TC increases exponentially with density of states. Here is the opposite. Not only it doesn't increase, it decreases, okay, with increasing density of states, yeah? So this in fact realizes ultra strong coupling superconductivity, yeah? We can measure the critical temperature as a function of filling factor and displacement field. I can project it onto this axis. And then I'm going to show you cuts along displacement field and filling factor directions, okay? So this is critical temperature versus filling factor at optimal displacement field. You can see two superconducting domes for electrons and holes around 2 holes per molar unit cell. I can measure simultaneously, in the same type of device versus the same trace filling factor, the superconducting coherence length, the Landau-Ginzburg superconducting coherence length, and it gives me this, okay? This, we can compare, the Ginzburg-Landau coherence length tells you roughly what's the Cooper pair size, and we can compare this with the average interparticle distance in our system. Remember, these Moire systems are extremely diluted because the lattice unit cell, the super lattice unit cell, is 100 times larger than atomic lattices. As you can see, the superconducting coherence length at optimal doping, okay, is of the same order as the interparticle distance. So Cooper pairs are as big as the average interparticle distance, okay? You can do the same thing versus displacement field, okay, at optimal doping. So at optimal doping, the Cooper pair size is similar to the average interparticle distance. Yeah? That's something which is very reminiscent of what happens in cold atoms at the BCS to BEC crossover. Okay, in the BCS limit, you have your Cooper pairs are much, much bigger in size than your average interparticle distance. In the extreme BEC limit, your molecules that be bound, both pairs are much closer together than the average interparticle distance. The BCS BEC crossover occurs when the Cooper pair size is similar to the interparticle distance. In 3D, there's a bound of 0.22 for this. In 2D, TBKT over TF in 2 dimensions is bounded by 0.125, which is reached at the BCS to BC crossover. Okay, and because we can measure the Fermi temperature and TBKT in our system, we can study this as a function of displacement field or filling factor. This is 0.125. You can see that we actually reach, TBKT over TF, which is values in excess of 0.1 with a maximum at 0.125. So magic angle twisted trilayer graphene is the strongest coupled superconductor that exists. Yeah? In this plot, I'm going a little bit fast because I'm running out of time, but in this plot, where you can put a variety of superconductors in terms of the critical temperature versus Fermi temperature, okay? This is telling you how strongly coupled a superconductor is. Unconventional superconductors are typically very strongly coupled, are in this region. Conventional superconductors are weakly coupled, are in this region. Magic angle twisted trilayer graphene is actually in this region. It's the strongest coupled superconductor that exists in the world. If the couplets have the coupling strength of magic angle twisted trilayer graphene, they would be well above room temperature superconductors. Okay? Another system has been recently realized that also reaches this ultra strong coupling. Now, in 1 minute, let me just tell you, okay, in a perpendicular magnetic field,
Pablo,
it is for superconductivity.
You can use a little bit more time. It's okay.
Just a minute or two. Superconductivity disappears well below 1 Tesla in a perpendicular magnetic field. Magic angle twisted trilayer graphene, because it's a 2-dimensional superconductor, allows us to put the in-plane magnetic field where you don't have the typical orbital effects, vortex formation, and look at the effect of a Zeeman field. Okay. In conventional superconductors, Cooper pairs form spin singlets. They are bounded by the gap. A Zeeman effect breaks Cooper pairs apart, spin up, spin down, so that by the time the Zeeman energy is equal to the gap, then the superconductivity disappears. This is known as the Pauli limit, okay? Which is about 1.86 Tesla for a 1 Kelvin superconductor, okay? This is again for BCS spin singlet superconductors. Now, we take our magic angle twisted trilayer graphene samples, we warm up samples, we rotate them so that they are, parallel magnetic field. We measure again, you can see very similar diagram as before, particular TC of 2.7 Kelvin here. The Pauli limit is 5 Tesla. So by the time you apply a 5 Tesla parallel field, superconductivity is long gone. You apply 10 Tesla and you can see that the system still superconduct in an extended region, okay? In order to determine the extent of the Pauli limit violation, we have to do temperature dependence measurements. So we measure the resistivity versus filling factor and temperature. This is the usual superconducting dome. Now add different parallel magnetic fields. You can see that even at 10 Tesla, we still have a finite superconducting dome. We can take now a particular density and do continuous measurement, temperature versus parallel field, okay? This is the filling factor of minus 2.28. We can take any threshold that we want for superconductivity, 10%, 20%, 30% normal state resistance. Well, it doesn't matter, all the same. These are parabolic contours, okay? Equal resistance contours. And you can extract then what is the Pauli limit, according to whatever ratio you want to extract. And as you can see, our system superconducts at much, much higher ratios, okay? In fact, the Pauli violation ratio is in excess of 3 for the system. Okay? So this actually, this appeared, no, this is about to appear. The possible mechanisms for Pauli limit violation, let me just mention this: strong spin-orbit coupling, FFLO type of physics. None of these apply to magic angle twisted trilayer graphene because graphene doesn't have spin-orbit coupling, and because FFLO states something that occurs only at very low temperatures, and it leads only to a small increment in the Pauli limit. We see a 300%, not just a few percent increase. Pseudo-gap physics, preformed pairs in the strong coupling regime can also lead to Pauli violation limit, but it turns out that we can vary our coupling strength okay, by an order of magnitude, while the Pablo bilayer ratio is always present, okay? So that means probably this also doesn't explain our Pauli limit violation. Moreover, none of those mechanisms explain the fact that in other region of parameters at smaller displacement fields, we see reentrant superconductivity, okay? Your resistivity, your zero resistance region decreases with paramagnetic field, but then at high field, it reappears again. That reentrant superconductivity, which we can see in the critical temperature or in the critical current, is extremely anomalous. It only happens in this type of radioactive compounds, superconductors, heavy fermions, with uranium family of compounds, and especially uranium tellurium-2 recently. These are nearly ferromagnetic or actually ferromagnetic spin triplet superconductors, okay? So it's very likely that magic angle twisted layer graphene where we can realize similar type of transitions between two regions, okay? With a zero field, a low field and zero field, and a reentrant region at high magnetic field. This is also related to not spin singlet superconductivity, either spin triplet or variations, linear superpositions of spin singlet and spin triplet superconductivity, okay? So with this, because my time is up, I want to end, and I just want to go to acknowledge my group members, all of you, and I hope we can get soon to this type of events, and thank you all for your attention.
Thanks a lot, Pablo, for this comprehensive presentation. We have time now. We have like 10 minutes for questions. I suggest we have some questions in the questions and answer chat. You can post more. I suggest that the people asking the questions turn on the video and ask directly the question to Pablo. Maybe we can get Abai to ask his question. Please go on. You can turn on the video if you want.
I'm not sure how to turn on. Oh,
okay, that's fine. So
anyway, so I'll ask the question. Thank you very much for the talk. So my question is about the correlated nature, correlated insulator of magic angle twisted bilayer graphene. Can you say something more about it? Is it Mott-like? Do we know if both charge and spin degree of freedom is gapped out there? And is there any topology involved there? Because it's formed out of Dirac bands.
Very interesting question. So this correlated insulator states, the exact and precise nature that leads to them is still under investigation, okay, theoretically. Now, theory is starting to sort of converge, okay? The details vary, but it started to converge the fact that indeed, this correlated insulator state appear because of a spontaneous flavor polarizing on some type, okay? So for example, you can have, at different filling factors, the nature of the polarization is different. The many-body ground state that flavor polarizes is different, okay? But let's say at filling factor 2 and -2, which is often the strongest correlated insulator states, there you have one of the favorite candidates by theorists is an intervalley coherent state, okay? Where you have two of these, Chern bands occupied, four, 6 or 2, depending whether you're at +2 or -2 of the Chern bands occupied, and the other 2 unoccupied, okay? And it's an intervalley coherent state, so it's a spin polarized state. You can have spin valley polarized states. You can have valley polarized states, without spin polarization. You can have many very different many-body ground states depending on the filling factor and the model, okay, and the conditions of this system. Do you have a small magnetic field out of plane or in plane, which is breaking certain symmetry terms, okay? The important thing to realize is that because of these multiple degrees of freedom, spin and valley, okay, you have competition between many-body ground states, and these are actually quite close in energy, okay? So you also have pneumatic states, charge-sensitive wave states, etc. So theorists are now trying to find out what, under what conditions small symmetry breaking terms lead to many-body ground states, choosing one or another configuration, okay? And this is not yet completely clear experimentally, but theories are slowly converging, okay? It seems like once you accumulate the different experiments, there's different experimental signatures in one or another direction, certain states are more favored than others, okay? And that's, but the important thing, I think the important thing I want you to get away from my talk today is that at each of these integers, there's a process of spontaneous flavor polarization, okay? And in some cases, that leads to an insulated state. In some cases, that can lead to pneumatic semi-metallic state, for example, other type of many body ground state. But these have to do with spontaneous flavor polarization of your bands, okay, of your flat bands.
Okay, thank you so much.
We have two questions by Guillaume. Maybe you can ask direct questions.
Hi, so I guess this is a little bit related to the previous question. So you talked about flavor polarization. Can you tell which flavor is filled first and then second and so on?
So we don't know yet, okay? Again, experimentally, I can tell you, we have some pieces of information. For example, at nu equals +3, okay, there is only one Chern band left. So the system is spin and valley polarized, okay? Because there's only 1 degree of freedom left, okay? Once you have filled all of the previous flavors, okay? The same thing happens at -3, okay? So that system at nu equals +3 and -3, it's clear that the system is spin polarized and is valley polarized too, okay? Because there's only one flavor left. So that's easy, okay? It is much more complicated what happens at nu equals +2 and -2, okay? Because there you still have 2 degrees of freedom left, and you can, flavor, valley polarize, spin polarize, or polarize in a, more global SU4 state. Okay, you can be spin valley polarized, or in a linear superposition of all of these things. Okay, so that is more complicated. From our initial transport experiments, when we applied a magnetic field out of plane or in plane to the nu equals 2 correlated insulator state, the resistance decreased. That led many people, including ourselves, to believe that the nu equals 2 correlated insulator state was spin unpolarized, okay? However, recent thermodynamic measurements with our collaborators, Shehalilani, independently by us and also by other groups, have shown that when you apply an in-plane magnetic field, the magnetization of the system, which you can measure in those measurements, with transport, we did not measure directly the magnetization, but with our chemical potential measurements, we can measure directly the magnetization via Maxwell relations. We see that the system becomes magnetized, okay, acquires a magnetization at a very small magnetic field very fast. So the system is either a strong paramagnet or a ferromagnet spin, okay, ferromagnet, okay? So now, more and more people are starting to think that the system may be at nu equals +2, it may be a spin polarized system, okay? That would be perhaps consistent, either spin polarized or a strong paramagnet easily polarizable, would be consistent with the Pauli violation limit, large Pauli violation limit physics that I have just described for the tri-layer case, okay? So the system becomes superconductor in the background of a system which is easily polarizable, okay? But we need more research to investigate all of this. It's not, experimental is not settled the question.
Mm-hmm. And I guess I have a second question. If you have time, you can answer. So you talked about superconductivity in the twisted bilayer magic angle and then in the trilayer graphene. Is the nature of the superconductivity different in the two systems?
Mm-hmm. Okay, so we don't know yet. Yeah? There are many similarities between the two systems. Superconductivity mostly occurs between filling factors 2 and 3 and -2 and -3, etc. Okay, it's also strong coupling superconductivity in both cases. The superconductivity, the TC is maximum when the density of states is minimum. Okay, so it's very unconventional type. Okay, and there is, here in this slide precisely, this, in this paper, in a subsequent paper, the Wisbarat group suggested that this alternating twist angle geometry, so this picture is for 4 layers, you can also have 5, 6 layers of alternating twist, okay, respects C2T symmetry, and they claim, the Wisbarat group, that the C2T symmetry is a key ingredient to realize this robust superconductivity, okay? So we still have to see if that is indeed a key ingredient. Okay, we have to make devices with 4 layers, 5 layers, etc. So I hope, soon either my friendly competitors or ourselves, we will build these devices and we will see if indeed one way of generating robust superconductors, Moire superconductors, is to use this alternating twist geometry. Okay, if this is essential and if this theory is correct, okay, then other theories that also like the C2T symmetry, but in this particular theory, this superconductivity is very similar to the mechanism for the bilayer, trilayer, etc., and it's due only to electron-electron interactions, and it's called skyrmionic theory of superconductivity. Okay, your Cooper pairs is actually a Bose condensate of skyrmion pairs actually in the system. So it's a pretty exotic mechanism for superconductivity. It remains to be seen if that's the mechanism.
Thank you.
Okay, thank you very much. We still have maybe a time for a final question. Juan, you raised your hand. Maybe you can ask your question.
Okay. Hello. Can you hear me?
Yeah.
Okay. Yeah. Hi, Pablo. Thank you very much for the very nice talk. So I have a question regarding it's a more basic question about the magic angle. So you have shown in the work with Shahal that you have like a non-uniform magic angle across your device, right? Mm-hmm. So when you measure in a device in a whole cross geometry the transport properties, I understand that what you have is like an average magic angle, and this is what emerged in the electrical transport measurements, right?
That's right. Okay.
So the second question is also device related. So do you have any influence of the edges on these whole devices, whole bar devices?
Very good. So let me. I thought you were going to ask a question directly about the previous stuff. So let me just make a further comment. So indeed, okay, the twist angle in these devices is not exactly identical across the entire device. Different devices have different degree of twist angle disorder, we call it, or twist angle inhomogeneities. Okay, the important thing is that in general, what we see is that for a device to exhibit magic angle graphene characteristics, meaning superconductivity, correlated insulator states, etc., the twist angle disorder has to be smaller than a certain amount. So roughly, since we know that this physics appears about 1.1 plus minus, 0.2 or 0.3 degrees, okay? When you characterize locally the disorder by a Gaussian in twist angle over your device, that Gaussian has to have a width of less than 0.1 or 0.2 degrees in order for it to exhibit these characteristics. We have seen that devices which have very high quality characteristics, very strongly correlated insulator states, clear superconducting domes, etc., tend to have narrower distributions of twist angle. We can measure locally. We can see that maybe for our best devices, the width of the distribution in twist angle is 0.01 degrees. Okay, and those are very high quality devices, and sometimes it's even less. Okay, so that's regarding what you said. Then with respect to the influence of the edges, okay? So we do not know yet, and it's a very interesting question. All the theory is always for infinite samples, but all the samples are finite experimentally, okay? So we have, some of the scanning probe techniques have investigated close to the edges, okay? We have not seen in an obvious way a strong effect of the edges, something that would lead us to think that anything in the physics is different. But of course, the moment you have, for example, a quantum anomalous Hall state, you're going to have, you have edge states, insulating bulk and edge states in the system, so you will see edge type of physics, and perhaps what happens at the edge might be relevant, for example, in terms of scattering for center types of, you can also realize quantum speed Hall phases here. They may be or not robust depending on what type of edge scattering you have, etc. Okay, so looking at the physics of the edges would be interesting. Something that I've told several theories, but I think it's something that probably has to come next generation type of theory papers, is the fact that this is a moiré system with a honeycomb structure, the moiré structure, right? So you can make theoretical studies analogous to graphene, where people make graphene nanoribbons, and depending on the termination of the graphene nanoribbon, zigzag or armchair, you have different types of edge states and different types of magnetism, etc. You could make moiré nanoribbons with different terminations of your moiré structure and see if it has one type of physics or another, okay? That thing, nothing is known theoretically as far as I know, and experimentally also, okay?
Okay, thank you.
Thank you very much. We have to move on. There are some questions that are still to be replied. I really direct you to the colloquium at the end of the session. We thank again Pablo for his very clear and comprehensive talk and discussion. Thanks a lot.
Thank you, everyone.